as one of the organizers, I'm sorry for not doing much work and then giving a talk instead. But the local organizers are doing a superb job, so hopefully I'm excused. So I recently wrote a paper with Jungwook in the audience, Junhee in Cliff Chung's group at Caltech, and Sung-Soo in Seoul. So you probably agree that the Post-Minkowskian expansion is one of the many nice things that happen when QCD meets gravity. When you actually compute something in the PM expansion, there are largely two directions. Either you try to compute the effective Hamiltonian after by integrating out the graviton exchange, or you try to compute the observables directly somehow. Well, the Hamiltonian is known to have some gauge dependencies, whereas the observables should be completely gauge invariant. Focusing on the observable side, let me raise a few simple questions. Well, in this talk, I'm not going to report any state-of-the-art multi-loop or higher spin computations. I'm instead raising a few elementary questions that, in my opinion, have been somehow overlooked over the years. So on the observable side, I can raise these questions. Is there a very simple way to encode all possible observables you can compute in your theory? A closely related question is what is the classical analog of the quantum S matrix? To simplify the questions, I'm assuming elastic scattering, where you can completely ignore all the subtleties coming out of unstable particles, decays, creation or annihilation of particles, energy losses. We are certainly not the first people to ask these questions. I'm sure there have been many related papers, but one particular paper where we learned a lot is the famous world-line QFT paper by Gustav in the audience and some others. So, sorry, yeah, Plevka and Steinhoff. So, yeah, they almost answered the question I raised in the previous page. And they go on to say that the Eikonal phase appears to be a generator for all observables of conservative classical scattering. Sounds great, but when we try to really understand what's going on in this game and the conceptual and technical meaning of this Eikonal phase as a generator, there were some fine points that we found hard to understand. So we wanted to clarify these fine points. After a lot of trial and error, we believe we settled down the question. And well, first in words, we suggest that we define the classical Eikonal as the generator of the canonical transformation that maps the incoming asymptotic states to outgoing asymptotic states. This notion is meant to be completely classical, and it assumes a Hamiltonian formulation of classical mechanics. And asymptotically, we assume that for a binary system, the phase space is that of a pair of free particles. By states, I mean some initial conditions and final configurations on your phase space rather than Hilbert space of quantum mechanics. And we definitely have a sign of unitarity. I mean, unitarity is roughly conservation of probability, and that is respected as a Liouville theorem in your classical mechanics. So how do you turn these statements into equations? One way to motivate this is to go back to this famous formula by KMOC that compute your classical observable from quantum mechanics. you compare the expectation value of some observable in quantum mechanics and take the h bar going to zero limit. Now, at least for elastic scattering, we assume that it's safe to take the log of the S matrix, and not surprisingly, call the log the Eikonal operator. Well, dismissing the states, we focus on the operators. In the Heisenberg picture, you can compare the incoming operator and the outgoing operator, and you do sort of expand this conjugation by the exponential operator to write the result in terms of these infinite series of nested commutators. A great thing about this series is that you have the right number of commutators and the factor of IH bars in the denominator. So the classical limit is kind of trivial. So you land on this formula. Although I use the quantum mechanics way of thinking about it as a motivation, you realize that you can just formulate this formula completely within classical mechanics. So it's understandable to a 19th century physicist. So yeah, we suggest that we take this as the definition of a classical Eikonal. In practice, in most theories, we cannot compute this classical Eikonal exactly, so we have to rely on perturbation theory. Then this whole formula can be expanded order by order, and higher order expressions are a little complicated, but that's not a big deal. As a side remark, in the source probe limit, and for non-spinning particles, you are essentially, or in zero SF approximation, you are essentially solving a central force problem. In that case, the classical Eikonal literally coincides with the radial action, which is better known and easier to compute. So you don't need to worry too much about it. Well, in a slightly more general context, when your Hamilton-Jacobi equation is separable, then you can compute something like radial action. But in full generality, when there is no symmetry to simplify the question, then you have to do a lot of hard work. And as I'm going to show shortly, the nth order term in your perturbation theory would require an n-fold integral, whereas the radial action is just a single integral, no matter how high you go in the perturbation theory. So I'm moving on to a slightly more technical part of the question. To focus on one particular aspect of this expansion to compute the classical Eikonal, although I was originally interested in the binary system, I'll focus on the single world line, forgetting about the other particle. And to simplify the problem even further, I'm going all the way back to the Newtonian theory, where your Hamiltonian is just the kinetic term plus a potential term. And you can do a perturbation theory if your potential is weak. So the proposal by the WQFT people restricted to this simple Newtonian model is the following. The Eikonal should be the sum of all connected tree diagrams with no external legs. And we have a whole bunch of vertices, which are basically the valence n vertices are the nth order derivatives of your potential. So the diagrammatics is fairly simple. And you recognize all the coefficients as the usual Feynman symmetry factors. But when we were studying these diagrams, we noted that one important element is missing. Which propagators should we use? You can think of, we are doing classical mechanics, so you can think of, retarded propagator, advanced propagator, or some linear combination of the two. we wanted to derive a fully rigorous and fully classical formula to compute these diagrams, including the precise prescription for the world line causality for the propagators. And the most naive, most honest, and least efficient way is to use the equation of motion directly. You know, it's Newtonian mechanics. You can solve the equation of motion order by order. So you can compute the observables. And then you trace back to the, you try to construct the Eikonal which reproduces the same observable. For low orders, working out the details is not a big deal. And I'm just throwing the answers for the first order and second order. And starting from the second order, you recognize the retarded Green's functions showing up. So we are using the initial condition as an input. So the retarded Green's function showing up is fairly natural. And of course, you can try to express your answers in terms of the graphical notation where you emphasize the world line causality using arrows. But something very interesting begins to happen at the third order. Up to the second order, there's not much you can do. Everything is more or less the same. But from the third order, you can see the difference. So for the third order Eikonal, you observe these three different assignments of the world line propagators, and they come with some non-trivial rational coefficients. Comparing this with the original formal expression for the Feynman diagrams with propagators not specified, then you recognize that this set of oriented graphs is a sort of refinement of this unoriented graph with some interesting sum rule taking place. So how does it generalize? So this is the answer for the fourth order, and it's the fifth order. Jungkook wrote a very nice mathematical code, but it got stuck at the eighth order. So it was definitely not too efficient. Anyway, the idea is clear. At any order in perturbation, we want to write down all possible oriented graphs, and we want to determine their coefficients. It's useful to put these symmetry factors in the denominator, as usual. But then the remaining task is to find a systematic way to determine these coefficients in the numerator. Using the equation of motion is certainly not the best way, so we wanted something better. And that brings us to the Magnus expansion. Well, apparently, Magnus expansion is very well known to some physicists and not so to others. So let me give a quick description. Let's say we have some time-dependent differential equation like this with some matrix acting on the vector, or you can replace the vector by anything with some linear structure and the matrix with any operator. In the scattering context, the vector is some functions on your phase space, and the operator is some vector field. The Hamiltonian vector flow on your phase space. Anyway, as long as you have this formal structure, you can try to solve this equation. We physicists call the result a time-ordered exponential integral. One way to give operational meaning is to do this Dyson series. But the Magnus series suggests that it is sometimes better to express the result with some exponential of something called capital omega. So in a sense, it's like a continuous version of Baker-Campbell-Hausdorff formula. Anyway, in the 1950s, a mathematician called Magnus came up with this very nice exact formula for the time derivative of this capital omega. I don't know how to prove it, but the proof is in the paper. Well, in practice, you can hardly solve it exactly. So again, you rely on perturbation theory. And using some formal coupling H here, you can turn this exact Magnus expansion to a recursion formula that builds up omega n with higher n. And the higher order terms have more and more commutators of your vector field. So how do you exploit this Magnus expansion in your classical mechanics problem? Well, we have the Hamiltonian equation of motion. And moreover, at least in the Newtonian theory, the kinetic term and the potential term is separated. So we employ the notion of interaction picture in the classical mechanics. So the potential is originally time independent, but once you switch to the interaction picture, it gains the time dependence this way. And your Hamiltonian equation of motion is now in the right form to apply the Magnus expansion. And using the isomorphism between the Lie algebra of Hamiltonian flows and the Lie algebra at the level of Poisson bracket, you can do some simple computations like this to see how the trees of the Magnus expansion grow out of this Magnus expansion formula. Yeah, I'm going to skip a lot of details, but there are certainly some simple ways to go from the Magnus formula with nested commutators to the tree graphs that are our final goal. When we were vigorously studying this formula, I mean, when we were working hard to find some nice formula for these coefficients of the tree graphs, we learned that some mathematicians already had the formula. So, I mean, one particular version is the one by someone called Murua back in 2006. And our work was twofold. One is we had to generalize this formula a little bit by considering the so-called rooted trees and non-rooted trees at the same time. And we also worked hard to, instead of trying to understand his original derivation, we found our own way of deriving the formula from this Magnus expansion. Anyway, we found the results that agrees with the known results in math literature. And there is actually more math, some Hopf algebra behind the Magnus expansion. Again, I don't want to get into the details, but let me just point out that this particular Hopf algebra was introduced by Galak, Ibrahim Ibard, and Wang Xiong in 2010, and it's different from, it's somewhat related, but not the same as the more famous Hopf algebra by Ghon and Kramer. Anyway, by learning and trying to understand the Hopf algebra, we learned some practical lessons. In particular, we discovered and proved some non-trivial sum rules that connect these unoriented graphs and the oriented graphs. And these combinatorial rules we found along the way were quite practical in that we combined all these ingredients and turned the whole thing into an extremely efficient algorithm, so that in the end, we wrote a mathematical code that compute all these omega coefficients up to the 12th order, which carry about 500,000 trees. And it's all done in less than an hour. Okay, so I spent a lot of time, playing with the Newtonian example, but of course our original motivation lies in the gravitational binary. So just to prove the case, we picked the first non-trivial example, which turns out to be the 3PM 1SF diagram. So in particular, the world line, the causality of the world line propagator really matters in these A-type diagrams. And yeah, so by summing up, taking the average of slightly different diagrams, we determined the relative weight between these two distinct types of world line propagators in this binary system, 2/3 and 1/3, and show that this is the right coefficient to agree with the previous results on the same diagram. Okay, I just was told that I have 5 minutes, so let me make a very brief comment on spins. Last night I was briefly thinking about giving some status report on spinning binaries, but in 5 minutes I decided to quit. Thankfully, there will be some talks on Thursday where you may get some updates. Sorry about that. So again, I'm going to raise a simple question. There are quite a few models for spinning particles in this macroscopic classical setup. Well, there is a distinction between field theory-based approaches and world line approaches. Within world line, we have these fermionic or supersymmetric way of introducing spins, or you have some bosonic models. Even among bosonic models, there are a few different members. Perhaps the most famous one is the spherical top by Hansen and Reggie. There is a related, but not quite the same model of using the covariant phase space with the angular momentum without the angle variables. There is another related model based on massive twister. So the question is, are they really different, or are they actually the same, but they are just in different disguises? In a paper from 3 years ago, we showed that the spherical top and the massive twister are equivalent at the level of a free theory. Does that mean that they should be the same theory even if we turn on the interactions? My first guess was that it should be obviously true, but actually after we started working out some details, we got very much confused. Another related question is, when we have two models that are different from each other, even at the free theory level, then which one should we prefer? On what grounds? I don't have the answer to these questions, but I believe the classical Eikonal should be helpful in streamlining the discussion. Okay, so I'm barely in time. Yeah, so I hope I convinced that classical Eikonal is a useful gadget in discussing the computations in post-Minkowskian expansion, or more broadly, any scattering problem. After working out the Newtonian example, we noticed that we have to take a few extra steps to go back to the gravitational binary and work out everything. So we have to combine the two world lines. And we should also include these graviton lags. And the external graviton lags accounting for the radiation would be even more interesting. Because we want a Hamiltonian formulation of graviton, whether using ADM or else. I forgot to write an independent line for the self-force expansion, but some of our formulas generalized to include graviton exchange look almost identical to the formulas found in the Salesforce papers. And we believe it's not a coincidence. There is a close connection between the two. And for 0SF, you can use the radial action, so you have to skip all these 3 expansion. And a similar, although less complete simplification is likely for the 1SF or 2SF, and I think we should work it out. As a final comment, with my student Hojin in the audience, we asked ourselves whether we can write down a simple classical Eikonal for the famous charge monopole scattering. And we learned that the naive attempt fails miserably. And we have some clues as to why that is the case, but I think we need more work to understand the whole problem in full detail. And then hopefully it will shed light on the scattering, charge monopole or dion-dion scattering problem, not only at the classical level, but even at the quantum level. Thank you.
Okay, yeah, so we have time for questions. Gustav first.
Thanks very much for the excellent talk. So you mentioned that you were only interested in elastic scattering, that you're not thinking here about dissipative effects. Could you, for example, include a retarded graviton propagator and have dissipation in that way? I mean, would this formalism allow for you to have now routed arrows on the gravitons as well as the world lines, and thus could you incorporate it that way?
Yeah, I think we can include the graviton. Both the internal ones and external ones, but we haven't spent much time working it out, so it may take a while. Jung took a few more steps than I did, but it's a work in progress.
Thanks.
Maybe I can ask a quick question myself. So the charge monopole, or the dion-dion scattering, I guess it's constrained to be on a cone rather than a plane?
Yeah, so that's one key element. So in the beginning, I mentioned that the classical Eikonal is a generator of the canonical transformation between the incoming phase space and the outgoing phase space. And one implicit assumption is that these two phase spaces are identical copies of the same free phase space. In the charge monopole or dion-dion setup, the angular momentum effect doesn't die off so quickly. So they are actually not equivalent, not identical. So that's where the problem comes from. And this plane to cone map may hold the key, but we haven't fully resolved it yet.
Any other questions for Sangmin? Okay, so let's thank Sangmin again.